Okay, today we are going to make the continuation of the first video that we made to define the principal moments of inertia of a rigid body. So we want to remember that on that first video we showed the relation between two inertia tensors that in the first video we named it as I tilde. That was for the indices I prime, j prime, and it was defined in terms of the principal inertia tensor as br prime, I prime, bs prime, j prime, I r prime, s prime. Okay, so this is the definition of one inertia tensor in the tilde coordinate system in terms of the main inertia tensor. Okay, so first of all, here you can notice that we are taking the transpose elements of the matrix B that we defined as an orthogonal matrix. So here in matrix notation we can express this equation as, for example, I tilde equals B to the T I B. Okay, remember that this T means transpose. Okay, so what are we going to do next? Well, what we are going to do in this video is to show that if the vectors that compose the columns of the matrix B are eigenvectors of I, then, well, this matrix is going to be a diagonal matrix. Okay, so we want to see what happens with that case. Okay, so actually looking at the elements of I are always going to be real numbers, and that I is of course a symmetric matrix. That means that if we change the indices, well, we get the same result. Well, that means that we can always going to be able to find orthogonal eigenvectors that correspond to the matrix I. Okay? Okay, so that means that if we are able to find that eigenvector, well, we are going to be able to write the next equation. Okay, this is the matrix equation that we can find. Remember that if a B is an eigenvector of I, that means that when we multiply this matrix times this vector, well, we are going to get just a multiple of that vector, because lambda here is going to be an scalar. Okay, perfect. So we can rewrite this equation in index notation as I R S Bs equals lambda Br. As you can see, well, this equation represents, for example, let's say that we choose R equals to 1, so we will get I1 prime, then 1 prime, B1 prime plus I1 prime, 2 prime, B2 prime plus I1 prime, 3 prime, B3 prime equals lambda B1 prime. Okay, so as you can see, this corresponds to the development of this product of matrices that we have above. Perfect, so we can just resume this product of matrices with this equation that I just wrote here. Perfect. Remember that looking at lambda is an eigenvalue of the matrix I. Well, that means that if we take the characteristic polynomial as the determinant of I r prime s prime minus lambda, the Kronecker delta r prime s prime equals to 0. Okay, this equation follows, looking that lambda is an eigenvalue of I, of course. Perfect. So we are going to see what happens with this equation that we have here. Remember something, the components of the I matrix, well, are real numbers. Okay, so what happens if we take the conjugate on both sides of this equation? Well, we are going to get I r prime s prime b s conjugate equals lambda conjugate b r conjugate. Okay? And what I mean with conjugate, I mean a complex conjugation, of course. Okay, perfect. So let me rewrite this equation again, but with another indices like this: I prime j prime bj prime equals lambda bi prime. Okay, so what we are going to do is to multiply on both sides of this equation by the factor bi prime conjugate. So this will be lambda bi prime conjugate like this. Okay, and on the other hand, we can, well, let me write again the equation bj prime bi prime like this. This can be seen as a bj prime I prime j prime bi prime conjugate, and here, well, we can use the eigenvalues equation, this equation that we have here, to get that, well, actually this one. We know that this is equal to this, so here we are going to get lambda conjugate, and this will be bj prime conjugate. Okay, and remember that we have this element, so this goes here like this. So we can rewrite this as lambda conjugate bj prime conjugate. Perfect, and let me rewrite this as lambda conjugate bi prime conjugate. I'm just switching the j for the I. Remember, there is no problem if I do that. Okay, so here we have this term over here, this term over here, and then we have that this is equal to this, and this is equal to this. So we are going to subtract both equations. This term minus this term is going to be equal to 0. So we are going to get 0 here. And then we can take a common factor bi prime conjugate, and just subtract lambda minus lambda conjugate. So this will be lambda minus lambda conjugate times bi prime conjugate like this. Okay, remember that the bi, well, they represent eigenvectors of the matrix I, so they cannot be 0 by definition of eigenvector. So that means that lambda minus lambda conjugate is equal to 0. Okay, so what do we want to show with this? Well, if lambda is a complex number, well, it can be represented as a plus bi, and then, well, we are going to have minus the conjugate of this complex number, but that is a minus bi. And we know that this equation tells us that it is equal to 0. So here we have that a minus a, well, is equal to 0, then bi plus bi is equal to 0. And that means that 2bi is equal to 0, making that b is equal to 0. So if we assume that lambda was equal to a plus bi, and we found that b is equal to 0, that means that actually lambda is just equal to a. So that means that lambda is, of course, just a real number. Okay, so lambda is not a complex number. That is what we wanted to show with this procedure. An important fact, because that means that the eigenvalues of the matrix I, well, are just going to be real numbers. Okay, perfect. So what we are going to show now is that if we take different eigenvalues for two eigenvectors, well, if the eigenvalues are different, this is going to mean that these eigenvectors are going to be orthogonal. Okay, so that is what we are going to show now. Okay, so let's introduce an eigenvector. Let's say it is going to be wi prime. This is an eigenvector of I. So that means that if we multiply I here, let's say I prime j prime, and let me change this w to a j. Well, this will be, looking that is an eigenvector of I, well, this is going to be equal to a constant mu times omega I prime, like this. This is the eigenvalues equation for the eigenvector W. Okay, perfect. Okay, so now we are going to look through this quantity. We are going to make something similar to what we have just done. And we are going to say that I, J, Bi, omega, sorry, W, J is going to be equal to, just by switching the Bi here, well, this is going to be equal to Bi prime mu omega I prime, like using the eigenvalues equation for W. On the other hand, well, we can say that looking that Bi is also an eigenvector of I, well, this can be seen as, let me rewrite it again, Bi prime Wj prime is going to be equal to Wj prime lambda Bj prime, like this. Okay, so it is just applying the matrix to each eigenvector to get different results. Okay, so again we are going to subtract both equations. In this case we are going to get 0, and in this case, well, we are going to get that lambda minus mu Bi prime Wi prime. Look that here I'm changing the J index for an I, because this can be seen as omega I prime lambda Bi prime. So there is no problem. That's why the index here, well, is the same in both quantities. Okay, so this equation is telling us that this product is going to be equal to 0, but remember that we mentioned that if lambda is different from mu, well, what is going to happen? Well, we get that Bi prime Wi prime is equal to 0, and this is the definition of orthogonality, right? We are taking the dot product, let's say that way, and we are getting 0. And that means that the eigenvector B and the eigenvector W, well, are going to be orthogonal. Perfect. Okay, and with that we can conclude that, well, those eigenvectors are going to form an orthonormal basis that will be made of eigenvectors of the matrix I. Okay, but we're here going to have 3 cases. We can have that for example, let's say in the first case that, well, yeah, looking that we are speaking in 3 dimensions, well, the matrices that we're working with are of order 3. Well, we are going to need, well, 3 eigenvectors for the basis that corresponds to the matrix I. So that means that we are going to get 3 eigenvalues. Okay, so we can have 3 cases. 3 eigenvalues are the same, or we can have that just 2 eigenvalues are the same or equal, or we can have that the 3 eigenvalues are different. Okay, so let's examine what happens, for example, if we have 3 eigenvalues and let's say that just 2 of them are equal. Let's say lambda 1 is equal to lambda 2. Well, in this case, what we are going to have is that the corresponding eigenvectors for each eigenvalue, well, they are going to form a 2-dimensional plane, okay, where, well, for example, we have one vector like this and one vector like this. Again, every point of this plane can be represented with a linear combination of these 2 vectors that are the eigenvectors of these eigenvalues. Okay, and actually any pair of eigenvectors or vectors that are orthogonal in this plane can be also part of that basis that is orthonormal that corresponds to the matrix I. Okay? Okay, so this is what happens when just two of the eigenvalues are equal. Okay? Again, remember that when we find the eigenvalues, we can associate those eigenvalues to a matrix that is a diagonal matrix, where the components of the diagonal are going to be actually those eigenvalues that we found. This is basic from linear algebra. If you have already taken some courses of linear algebra, maybe you saw these topics in diagonalization. But if we examine the case when these three eigenvalues are equal, we can just rewrite this as lambda equals 1, 0, 0, 0, 1, 0, 0, 0, 1, which is of course the identity matrix. Okay, so this is the case that we have when the eigenvalues are all equal. And of course, if these three eigenvalues are different, we are going to have that the corresponding eigenvectors for these eigenvalues, they are going to form an orthonormal basis. Okay, perfect. But actually in the three cases, we see that the sets of eigenvectors always form an orthonormal basis. And recall that these are eigenvectors of the matrix I. Okay, so here is where we remember again the definition of the I tilde matrix that was B, T, I, B, like this. And again, looking that B is orthogonal, we have that B to the T is equal to B inverse. So that gives us B inverse I, B, like this. And looking that due to this equation that we have here, this one, and that we have shown that the columns of the matrix B form an orthonormal basis, that means that this product over here is going to be a diagonal matrix. Again, this is a very famous theorem for linear algebra. It says that, if this matrix is orthogonal and the columns of this matrix are eigenvectors of I, that means that this product is going to be a diagonal matrix. Okay, so that means that I tilde is diagonal. Perfect, and this is going to be very, very, very important, because that means that, for example, if we can write I tilde like I tilde 1, 1, 0, 0, or in this case it's just necessary one index, 0, I tilde 2, 0, 0, 0, I tilde 3, like this. In this case, we are going to define the elements of the diagonal as the principal moments of inertia. Okay? These elements are I tilde 1, I tilde 2, and I tilde 3 are the principal moments of inertia. Okay, so remember that if you develop this product in linear algebra, you get that the matrix that you get is composed of the eigenvalues in the diagonal components, like this. So this is equal to I tilde. So that means that these elements that we have here are actually the eigenvalues of I. Okay, so that means that I tilde is a diagonal matrix and its components are the eigenvalues of the matrix I. Okay, another thing that is going to be important to mention is that remember that the I tilde tensor was defined from another basis. Well, yeah, it was a different basis from the I tensor. Okay, remember I tilde had the basis EI prime tilde, and the I tensor was from the basis EI prime like this. Okay, so looking that we defined the principal moments of inertia through this I tilde matrix, these vectors E1 prime tilde, E2 prime tilde, and E3 prime tilde are going to be named as the principal axis. Okay, so just let me write it here. And by now, well, these are the important concepts that I wanted to show in this lesson, that are the principal moments of inertia and the principal axis. Okay, and with this, we can give a new perspective about what this I tilde tensor means. Remember that we had the rigid body like this, and we defined first, well, a coordinate system primed, x prime, y prime, here, and then we said that we can introduce a different coordinate system that corresponds to the tilde tensor. Let's say x tilde, y tilde. Okay, these are just two different coordinate systems that are related with a matrix that changes the basis from one to another one. This topic, we saw it on the first video of the inertia tensor. But the important thing here is that it turns out that for this origin, well, we can find an inertia tensor so that the matrix associated to that inertia tensor is a diagonal matrix, like this. Okay? And so that the vectors that compose this coordinate system that corresponds to that tensor are going to be, well, the principal axis for this origin O. Okay, this is the important thing. So if we define a coordinate system on a certain point from the rigid body, on that same origin, we can find another coordinate system that will give us another inertia tensor, so that that inertia tensor can be represented with a diagonal matrix. And that, well, for that inertia tensor, we will have the principal axis. Okay, that will be the important idea about this change of basis for the inertia tensors and for rigid bodies. Okay, perfect. So this will be a good place to finish the lesson.